All right. So this next item is a really important formula conceptually. Okay, it's called Coulomb's law. Coulomb was a French physicist. The unit for electric charge is the Coulomb, named after this guy. You see a constant in this formula. The constant here is just like in the gas laws. To turn a proportion to an equation, you put a constant in, right? The F is the electrostatic force. Another way to say that, if you're not sure, you might want to jot this down as well. It's the force of attraction if you're talking about oppositely charged particles, or it's the force of repulsion if you're talking about the same charges, right? In the homophobic world of physics, the opposites attract and the likes repel. So if you're talking about charged particles, there is a force of attraction or repulsion. We'll just call that an electrostatic force. What does that force depend on? Well, it depends on two basic things, arguably three, but let's say two. One is the charges involved. So Q1 and Q2, those are the charges on the two things that are repelling or attracting. Q1 is the charge on one object, Q2 is the charge on the other object. Notice that those are in the numerator of the formula. So what does that mean about the charge on an object and the force of repulsion or attraction? They must be directly proportional, right? So if you double one of the charges, you're going to double the force of attraction or repulsion. The second variable besides the charges involved is the distance between them. In this formula, the distance is represented with the letter R. I've also seen the formula. You could just use the letter D if you want. So it can be over D squared if you prefer. It would be a lowercase d. Okay, but notice the D, notice two things about distance. Number one, it's in the denominator. So which means it's an inverse relationship. But it's not just D, it's D squared or R squared. So that's actually called an inverse square relationship, right? What does that actually mean mathematically? Well, if it were just an inverse relationship, what would tripling the distance do to the force? If you make particles 3 times as far away from each other, the force would be 1/3 of the original force, if it were just an inverse relationship. But it's an inverse square relationship. So if you make the particles 3 times as far from each other, the force will not be 1/3, it will be 1/9 of what it used to be. So when you look at it that way, because it's a square, inverse square, distance is a more important factor than charge when it comes to the force, right? Doubling a charge will double the force. Doubling the distance will make the force 1/4 as big. So the distance has a bigger effect on the force. I said I'm not going to, this is a formula very important because we're going to refer to it a lot conceptually, but we're never going to calculate anything with it. Okay, so you don't really need to know Coulomb's constant. We're not going to use the formula. What you do need to know is that the force of attraction or repulsion depends on two things, the charges and the distances involved, and the charge is directly related in the distances inverse square relationship. If you see the formula, then you don't have to memorize that. You can just see it in the formula, right? If you understand how formulas work. So types of intermolecular forces. We're kind of going to go from the strongest to the weakest, kinda. The strongest one is actually not on my notes, so you're going to want to add it at the beginning. The second strongest we're going to call ion dipole. So the strongest you'll call ion-ion attraction or ion-ion interaction. That'll be the strongest type of intermolecular force. Some books, some authors would not include that as an IMF, an intermolecular force. Others do. So we'll put it in there. Its name is kind of self-explanatory, isn't it? If you have two cations, there will be a force of repulsion between them, right? If you have an anion and a cation, there'll be a force of attraction between them. So all we're saying is the force of, let's talk about attractions here. Okay, we won't talk about repulsions, we'll talk just attractions. The force of attraction between particles is greatest when the two particles are both ions, right? That's what that means. And why is that? Well, Coulomb's law said the force depends on charges, and ions have like a whole charge, don't they? The charge on a sodium ion is +1. Water molecules, well, those are polar, right? Water is polar. There's a positive side and a negative side to a water molecule, but those positive and negatives in water are not complete charges. They're partially positive and partially negative. Water is not ionic. Water is polar covalent. So the charges on ions are larger and more concentrated charge than the ions in a dipole. Do you understand what I'm saying there? So therefore, Coulomb's law, if both charges, Q1 and Q2, are ions, that's going to be a really strong force. Okay. The second strongest, and this is in some books, this would be the first intermolecular force, is the force between an ion and a dipole. Now, there's a very specific common situation where this occurs. If you're dissolving ionic compounds in a polar solvent, dissolving ionic compounds in a polar solvent, this will occur. A less technical way of saying that, if you're dissolving a salt in water, this will occur, right? Water is not the only polar solvent, but it's a very common one. We just said that the forces between ions is the strongest force, right? Sodium chloride, table salt, is full of a whole bunch of sodium and chloride ions attracted to each other. But you put that in water and it dissolves. The water somehow pulls those ions apart from each other. How can that be? Those ions are strongly attracted to each other, right? So something is overcoming the attractive forces within the salt. What is it? Well, it's an ion dipole force. Let's draw for ourselves a water molecule, okay? But I want you to, I'm going to take a small detour here. I think I forgot to do something with you that I did in the morning class. Let me spotlight this. Okay, if you want to just put this on the side of what we're talking about, it's related to what we're talking about here, but it's a little bit of an aside. I just asked you to draw a water molecule. In the water molecule, does everybody know how it's actually shaped? Right, we write the formula H2O. One of the problems with doing this topic in grade 11 instead of grade 12 is that we don't know how to predict shapes of molecules. You need to know about shapes to talk about whether molecules are polar or not. So water, I just want you to know the shape. Water, there's an oxygen atom with 2 hydrogen atoms attached, and they're attached in that shape, that V shape. It's about a 104, 105 degree angle here, okay? Why it's shaped like that, well, hold on till grade 12 and we'll talk about that. Another molecule I want you to know the shape of is carbon dioxide. Carbon dioxide is like water in that it has 3 atoms, but its 3 atoms are in a straight line. There are double bonds instead of single bonds, but that's not really important. It's the fact that there's a straight line is what's important. I know. If you think about the bonds for a minute, your lesson, the ed puzzle that I gave you on polarity and nonpolar polar bonds, it was about bonds, not about molecules, right? Is the OH bond polar?
Yeah.
That's one you shouldn't even have to look on a chart to find out. You should just know. Yes, it's polar. Why is it polar? Because oxygen is the second highest electronegative element. Hydrogen is not even in the top 4. So there's likely going to be a difference between them, but it's not huge, but it is significant. So this is a dipole. And since oxygen is more electronegative, we'll draw an arrow pointing up at oxygen. Oxygen is pulling electrons away from hydrogen. The same thing happens over here. Now, those arrows that I've just drawn in a math or physics class, those would actually be called vectors. Okay, if you've taken physics or maybe some advanced math, you might be familiar with vectors. Then you can think of them as vectors. For those who've never heard of vectors, then just think of it like this. Suppose somebody here is pushing up at oxygen. Somebody over here is pushing up at oxygen like that. They're pushing at angles up at oxygen. Would the oxygen move if they were pushing with enough force?
No.
Would the oxygen move if 2 people were pushing up like that? The answer should be intuitively yes, right? If they were both pushing up like that, yes, the oxygen would move. Right? That should be intuitive. What direction does the oxygen move if those 2 hydrogens are both pushing up like that? It'll move straight up. Okay? Sort of like if you have a wagon and you're pulling at that direction on the handle of the wagon, does the wagon move? Yeah, it moves this way, doesn't it? Right? Even though you're pulling up at an angle. For those who've studied vectors, you know that when you pull up like that at an angle, there's a horizontal component to what you're doing, and there's a vertical component to what you're doing, right? The vertical component isn't big enough to lift the wagon up. The wagon weighs too much. But the horizontal component pulls the wagon horizontally. Similarly, over here, these 2 hydrogens pushing up, there's a horizontal component to both of them, but look, they point at each other. So what do? Those horizontal components cancel each other out. But there's also vertical components, but the 2 vertical components are both pointing up. So they don't cancel each other. In fact, they add to each other. So that's why there'll be an overall, what I just described is the vector way of doing it. If you've never understood or took vectors, never studied vectors, just, I think it was intuitive. If 2 people pushed up like that, the O would move up, right? Oxygen was more electronegative. So we say there's a partial negative charge on oxygen. There's a partial positive charge down here. Is everybody familiar with that Greek letter?
No.
Okay. In English, we write a capital D. In Greek, you write a capital D like that. In Greek, you call it delta. In English, we write a lowercase d, and in Greek, that's your lowercase d. So it's the letter delta, and just like our capital D and a lowercase d, there's a capital delta and a lowercase delta. The capital delta usually means change in something. The lowercase delta here was going to mean partial. So we say partial negative charge, partial positive charge. That's why water is polar. It had 2 polar bonds, right? And then the whole molecule is polar. Now look at carbon dioxide. Are its bonds polar? Can you use the same reasoning without looking at a table? Are the bonds polar? Yes, right? Again, because oxygen is number 2 of electronegativities, the second highest. Carbon's not in the top 4. So there's probably a pretty big difference between them, isn't there? Do you get what I'm saying there?
Mm-hmm.
You could go look up the electronegativities and subtract them and say, yep, it's polar covalent. Or you could just use that reasoning. Oxygen is one of the top 4, carbon's not. So it's either going to be ionic or it's going to be polar covalent. Because they're close together on the periodic table, the difference is not going to be huge. So it's going to be polar covalent, right? The farther they are away from each other on the periodic table, the bigger the difference would be. Do you follow that logic? Hisham, are you good with that?
Yeah.
So this bond is polar. What direction would I draw the arrow? Towards who?
No.
Towards the more electronegative element, so towards oxygen. But then that makes oxygen partially negative and carbon partially positive. What about on the other side? Isn't it identical on the other side?
Mm-hmm.
So can you see what's going to happen now? Carbon dioxide has polar bonds, but it's shaped differently than water. What's going to happen because of its shape? The oxygen moved up because hydrogen pushing and hydrogen pushing moved it up. Somebody over here is pulling this way, somebody over here is pulling this way, and they're pulling equally hard. What happens to carbon in the middle? Does he, okay, he doesn't split apart. Does he move? If he doesn't move, which I agree, why doesn't he move? Because those two forces will just cancel each other out, right? Why do they cancel? Because they're in opposite directions and they are equal, all right? If they're pulling in opposite directions and they are equal, they'll cancel each other out. So even though the molecule has 2 polar bonds, this molecule is non-polar. The 2 dipoles, the 2 polar bonds, cancel each other out. You might want to say that to yourself. Over here, the water molecule is polar. It also has 2 dipoles, but they don't cancel each other out because the shape of the water molecule is different than the shape of the carbon dioxide molecule. So although it's pretty easy, if you give me a table of electronegativities, to tell you whether a bond is polar or not, to decide if a molecule is polar or not, you need to also know about the shape, don't you? And there is the problem. In grade 11 chemistry, you don't know the shapes of most molecules. You'll know these 2 because I've asked you to memorize those 2, but other molecules, whether they're polar or not, might depend on their shape, and I don't know their shape. So how could I tell you whether they're polar or not? Well, let's use some reasoning here, right? Suppose a molecule has no polar bonds at all. So a molecule has a whole bunch of bonds, but none of those bonds are polar. What would you then conclude about the molecule? Polar or non-polar?
What?
If none of the bonds in a molecule are polar, will the molecule be polar or non-polar?
Non-polar.
No. If none of the bonds are polar, is it logical it can't be a polar molecule then?
Because there's no charges.
There's no dipoles,
Yeah.
right? We're not talking about ionic compounds. Okay. Does that seem logical?
Yes.
You might want to jot that down. If there's no polar bonds in a molecule, the molecule cannot be polar. What if there was one polar bond?
It can be.
Could you conclude something about that?
Yes.
Conclude? it would have to be polar, wouldn't it? Why? If it only has one polar bond, why would the molecule then have to be polar?
There's no way it can cancel.
What if there's like 3?
Hold on. If there's only one polar bond, there's no way it could get canceled out. So with only one polar bond, a molecule must be polar. And when there's more than one polar bond,
It could be equal.
then it depends on the shape, doesn't it? When there's more than one polar bond, it could be polar or it could be non-polar, depending on the shapes. However, we might still be able to squeeze one more thing out there. What if there were 2 polar bonds, but they were different? So in these 2 examples, the 2 polar bonds were identical, right? There's 2 OHs or there's 2 COs. They were identical. It depended on the shape, whether it was polar or not. What if there were 2 polar bonds in the molecule, but they were not identical? One was a stronger dipole, the other was a weaker dipole.
It has to be polar.
Then it would have to be polar, wouldn't it?
Mhm.
Because if there's only 2 dipoles in the molecule and they're not equal, they could not possibly cancel each other out, could they? Because they're different. Hisham, are you good with that? I don't have my glasses on. I just see this blurry thing over there, and you're kind of looking at me. So I'm going, does that mean he doesn't get it, or? Okay.
I should have done this on another page. My notes are so messed up now.
What's that?
I have to fit everything in the side.
We have a lot more to do.
Oh, no.
All right, let's go back to that PowerPoint.
Okay, then that's fine.
So when you put, actually, before I go back to the PowerPoint, no, we'll come back to it. Let's do this first. So we just said an ion dipole attraction occurs when you have an ionic compound, cations and anions, dropped into a polar liquid. Then the polar liquid molecules will be attracted to those ions, right? In the water molecule, what part of water would be attracted to sodium ions? In the water molecule, which part of the water molecule is attracted to sodium
The
ions?
oxygen.
Sodiums are positive, so the negative oxygen would be attracted to sodium ions, right? If there were chloride ions also, sodium chloride, table salt, then wouldn't it be the hydrogen atoms in water that would be attracted to the chloride ions, right? Opposites attract. If you can have several water molecules pulling on a sodium ion and several water molecules pulling on a chloride ion, even though the sodium and the chloride are very strongly attracted, an ion and an ion, if you had several water molecules, dipoles, pulling on those ions, do you think they might actually be able to separate them? Remember, ion dipole forces are weaker than ion-ion forces. But if you had several of these water molecules, all of them pulling on the sodium and several pulling on the chloride, could these weaker forces actually pull them apart?
The tag team.
Yes, they could, right? Was it Gulliver's Travels? Is that what it was with the Lilliput or something?
The what?
You guys, no, Gulliver, wasn't that? Am I thinking of the right book? The big giant guy and those little people, and the little people all tied him down and stuff like that. Anyways, salt dissolves in water, even though salt has very strong ion-ion attractions that say we don't want to dissolve. The weaker ion dipole forces between water and the ions in the salt, there's more of those. So they're able to work together and pull them apart. Some salts dissolve, other salts don't. Salts that don't dissolve in the water, why don't they dissolve? Because the inner forces between the ions must be too strong. The ion dipole forces aren't strong enough, right? So some salts are highly soluble, some salts are not.
So you know how when you like heat like the warm water up, the solubility of it goes up, like you can dissolve more. Is that because like the heat is like breaking the?
So the question at home is, the solubility goes up when you raise the temperature. Why is that? That's kind of a complicated question, but one possible thing to consider is that the ions in the salt, as you warm up the liquid, they also start moving around more. And then the ions in the water molecules are moving faster and colliding more. I think that might be related to it. Okay. All right, do you recognize these three bullets here? Do you recognize them? Isn't that just Coulomb's law again?
Yeah.
The magnitude of the ion's charge, that's Q1. The magnitude of the dipole,
Q2.
that's Q2. And the distance between them, that's R or D, right, in the formula. Sketch that. So the gray things are dipoles, right? Positive and negative ends to them. The red thing is a cation. The green thing is an anion.
You have to color them?
You don't have to color them, no, but so when you put the salt in water, the ions get pulled apart. And as they're pulled apart, do you notice how these gray things are oriented, just like we talked about a minute ago? The negative sides are pointing at the positive guy in the middle. The positive sides are pointing at the negative guy in the middle, right? Make sure when you sketch that, you're doing it in that right way. Let's do the same thing, but this time with water molecules. Start by just draw for me 4 or 5 or 6 water molecules showing intermolecular forces between them. Okay, I'll start you off. So here's one water molecule. And I'm not going to do this for every single one of them, but I'll remind myself that oxygen is slightly negative, the hydrogens are slightly positive. So if you just have pure water, then there's a neighboring water molecule, right? A neighboring water molecule might be oriented like this. Why would it be oriented like that? Because now its positive hydrogen would be attracted to this guy's negative oxygen. To show that attraction, I'll just put a little dotted line. Well, over here, there might be a water molecule like that. Now, as we'll see tomorrow, probably, oxygen can actually do that dotted line thing twice. Hydrogens can only do it once, but oxygen can do that little dotted line twice. So this oxygen here can be attracted to that positive hydrogen, but also to that positive hydrogen. And now there's 2 H's over here. I could do another water molecule like that. Is this making sense to you? What are the solid lines in my diagram?
Covalent bonds.
Covalent bonds. And what are the dotted lines?
Hydrogen bonds.
Well, you're getting ahead of me there, but let's call them right now intermolecular forces. As we'll see in a bit, they're dipole-dipole forces. And as we'll see in a bit, they are in fact hydrogen bonds as well. But for now, we'll just think of them as intermolecular forces. And now let's do salt water. And for the salt water, we'll put a sodium ion. It doesn't have to be table salt. We'll do sodium and we'll do chloride. So sodium is slightly smaller than chloride, so I'll draw it like that. Sodium's positive, the oxygen in water is negative. So when you put the sodium in the water molecules will be oriented around it like this, won't they? In fact, you'd probably end up with 6 water molecules surrounding every sodium ion. One of those waters would be above the ion, one would be below the ion, and 4 would be around the middle. It would form what's called an octahedral geometry. We won't worry about that. The chloride ion over here would also be surrounded by water molecules, but this time, because chloride is negative, it'll be the hydrogens in the waters that are attracted to it. So you draw your hydrogen atoms oriented towards the chloride. This kind of diagram is called a particulate diagram, and the AP exam has a fetish for this kind of thing now. It likes you to draw these things. Like they'll throw these in multiple choice questions, and they'll put little letters on the dotted lines, A, B, C, D, and they'll go, which one of these is a hydrogen bond or something? Or they'll ask you to draw an ion like that. You have to draw it in the right way. Now, that ion is now surrounded by water molecules. There's a name for that, okay? The ions, when they're surrounded, we put AQ beside their symbols. We say they're aqueous, right? Up till now, we've just sort of said aqueous means in water. In fact, aqueous means not just in water, but in water and surrounded by water molecules. When it's surrounded by water molecules, we say the ion is now hydrated. Okay? Hydrated. If I told you to get hydrated, you'd probably go drink some water. Hydrated. When the ions are surrounded by water molecules in the way we just drew them, the ions are hydrated. You don't have to use water. You could use any polar solvent. It would do the same thing. So there's a more general word. Instead of hydrated, you could say solvated, like solvent, S-O-L-V. So solvated would be the more general term. If the solvent is water, it's hydrated. If the solvent is not water, you could say the ions are solvated. And of course, if they're solvated and you listen really carefully, what will you hear above the solution? You'll hear, hallelujah, hallelujah, because I've been solvated. You get it? Solvated? Oh, God. Nobody here go to Bible school. Nobody here go to Bible camp.
I'm Jewish.
Yeah.
Oh, geez. Okay.
I went to Bible camp and I still like
Salvation, salvation. You get it? Oh, thank you, Devin. Devin's nodding at me. Okay. I'll stop here. This is not obvious to everybody, but when you form those forces of attraction, when the water molecules surround the ions like that, that's an exothermic process. You have to think about it to figure out why it's exothermic, okay? If you think about it, you don't have to memorize it because it'll make sense. Suppose you want to pull apart two things that are attracted to each other. You want to pull them apart. Will that be endothermic or exothermic? I think this is obvious. Prove me right. If you want to pull apart things that are attracted to each other, you need to pull, don't you? If you need to pull, you are putting energy in, aren't you? Which means pulling them apart would be endothermic. You have to put energy in to break the bonds. Is that obvious to you when you think about it?
In bio about the enzymes,
I-
whatever, and
I-
enzymes and energy break apart.
Is this making sense to you? Like not
Yes.
memorized, it'll make sense. If I want to break the bond, I got to put energy in to do that. That's endothermic. Well, then the opposite of breaking the bond would be forming the bond. Then if it's the opposite, it won't be endothermic, it'll be exothermic. I think breaking bonds is obviously endothermic. Then when you think of it like that, the forming bonds must be exothermic. Say again? So from an energy perspective, if you want to say why is it exothermic, if the bonds form, it's because they must be more stable than when they weren't formed. If they're more stable, Jackie, thank you. If they're more stable, they're going to a lower energy state. To go to a lower energy state is to lose energy, right? So when things have less energy, they're more stable. So since these bonds form, whatever's forming is more stable. So if it's more stable, it must be lower energy, right? All right, I'm going to stop there. We're going to talk about dipole-dipole interactions. We've already drawn it, the water molecules attracted to each other. This one will be weaker, won't it? Why is this one weaker?
Are we doing this tomorrow?
This one's weaker because there's no ions, which are pure charge, right? There's just partial charges involved now. So in terms of Coulomb's law, Q is going to be smaller, right? So we'll talk about this tomorrow. We'll also see hydrogen bonding tomorrow, right? In this context.
So this is when chemistry and bio kind of come together.